All right, today's question is about implementing an LRU cache. So a high-level overview of a cache is, usually you have some sort of a CPU that needs to do work, and to do work, it needs data to do work on. And you probably get some data from this big, slow storage device, and it pulls in data and gives out the results like this. But this is very slow, right? So you want to mitigate this, you have some sort of a cache in between. It's small, fast, but more expensive. And you have this cache. And now, instead of asking this slow storage device, the cache can be the middleman. So the CPU asks the cache instead. And if the cache has an answer, it can reply on behalf of these bigger storage devices. But if it doesn't, there's some sort of a background process to make sure that this information is fed into the cache so that, in the future, when they ask, we have the correct answer. Okay, so in this question, they tell us we want to implement get and put. And we want to try and aim for constant time for both of these operations. So usually with that, you're already thinking maybe something like a hash map. But the difference with this is that with a cache, we have some sort of a capacity, because as we're putting things into our cache so that it's being useful. Once it's full and we want to put something new in, we now have to choose which of these data should we forget about to make room for this new piece of data. So one such way is least recently used, which is what we're going to be implementing today. So assuming we have a capacity of 3, and this is like a series of puts and gets, it's a little bit of a spoiler, but so we come in and we want to put in a triangle in our cache, and then here, we'll say that going this way is from least to most recently used. So we start off here, and then we put in this square here, and this square, we used it more recently than the triangle, so it's ahead of it, and then we have this star. And at this point, our cache is full. Then it asks us, we want to put in this 0. So now we have to choose the least recently used one, which is this triangle. And then we'll evict it. So we kick it out. And then we put this 0 in. And we're going to put it here because it's the most recently used. And now when it queries to say, do we have a square? We still have it in our cache. So this is a good call. And then here we want to put in a squiggly. And again, because we want to put it in, but it's already full with 3, we're going to evict this square. Okay, so we evicted this square, and now we put in the squiggly is here. And now we ask, is there a triangle? At this point, our triangle is long being evicted, so all we can say is that no, we don't have a triangle, and maybe some sort of a background process kicks off to eventually move the triangle into our cache, so that when they ask in the future, we have it. Okay. So now there is this star, and then this star, we already have a star here, so this is more of an update, really. And what it does is, when we update it, we are technically still using it. So even though we are updating it, we're still using it, so we move it to be our most recently used. And then at the end, they query for our square, and the square is gone at this point, so here we also say negative. We don't have a square. Okay, so that's an example of LRU, and now we have to implement it. So again, we wanted to try some sort of a hash map, but then we also have to keep in track of least to most recently used and have some sort of elements shifting around. And what we'll do in this case is we want to think of something like a linked list, right? Because as we're shuffling these elements around, if we have a linked list that are connected to each other, if we want to remove this middle element and put it to the end, all we have to do is, just hoist it, put it at the end, fix up these pointers, and then create these new ones, and then you're done, right? So that still counts as constant. Versus if you have something like an array, and you want to remove like a middle element here, what happens is you remove this, but now you have to individually shift each element over, something like that. So that is a lot slower, and we're no longer talking in constant time. Okay, so we want to combine some sort of idea from our hash map and from a linked list. So let's go and try coding this out. So to start off with, we're going to have some sort of an idea for a node in our linked list. So let's have a node. And this node will know its key and value, as well as its previous and next. So this will be a doubly linked list. Okay, so let's create some sort of a constructor. Cool. All right, and we're going to get in some sort of capacity. So let's keep track of our capacity here. And this capacity equals capacity. Okay, and now we want to call get. So get, we need to know if we have something in our cache. So this is where we will need some sort of a hash map. And this hash map is going to map from our key. So we know that our keys are integers to a node, because with this node, we can return the value. Okay, so we have some sort of a map, and we can initialize it to be capacity. That way it doesn't have to grow again throughout our use of LRU cache. We already have allocated it, the capacity, and we'll never go over it. Okay, so there is our map. And now here we can ask ourselves if map contains key of this key, then we can, read our node. So we'll define this function later, and then we can return the value. So the reason I don't just immediately pull from our map is because, remember, when we're reading, when we're using our elements, we want to mark it as, that it's most recently used so far. So we have some sort of a private node read that takes in a key, and what we wanted to do is we want to return the node of this key. This key must exist, and we want to mark this node, or I guess shift this node to be most recently used. So it's the tail of our linked list. Okay, so we have some sort of a read, and then if we don't have our key, then we just return -1. And here in our put, we're going to have a couple of different cases. So one, we could be updating an existing key. Otherwise, it's a new key. And then in this new key, we have to check, do we need to evict anybody? So are we full? Otherwise, we can just create our new node and then append it to the end of our list. So it's the most recently used so far. Okay, so updating an existing key. We can do something similar to what we did for get. And here, what we'll do is we'll read this key to get our node, and then we'll just update the value, and that'll be the end of that. Okay, next, how do we know that we need to evict? Well, that will probably be because our capacity is now equal to 0. And then we will evict. And because we evicted, our capacity will grow again. And then now we need to create our new node. So to create our new node, that costs a capacity. So now our capacity goes down again, but we are allowed to create a new node. So new node with this key and value. We'll append it to the end of our list, and then we'll make sure that we update our map so that this key is associated with this node, so that later when the client asks for it, we can get it fast. Okay, so that should be the end of that. We'll figure out how to evict soon, and we'll figure out what this append does. Okay, so here we have some sort of a private void append for a node. And now the method that I'm going to show you for a doubly linked list is one where it's a lot easier to write. There's less edge cases to worry about. But the trade-off, there's always a trade-off, is that we are going to be creating 2 extra nodes. So this is a trade-off because usually you want your cache to be small, or it's like you have some sort of restrictions on how big your cache can be. So you really can't waste that space for 2 extra nodes. So this is totally doable without these 2 extra nodes, but this is just an easier way to code. If you want, you can go ahead and try taking these out and getting all the edge cases correct. Okay, so the purpose of these 2 kind of like bogus nodes is that they allow me to always have something in my linked list. So our linked list starts like this, and then when we start putting in our items, I can always be sure that the previous is not null and the next is not null because I have these 2 bogus nodes protecting the start and the end. So I never have to worry about edge cases. Okay, so we'll link these 2 together. Tail.previous is equal to head. And now when we read, we want to get the actual node by reading our map. And then what we want to do is we want to mark it as it's most recently used. So for example, if we had x, y, z, and we're reading x, then instead of x here, by the end, we want to move it to be here, our most recently used. So what we want to do is we want to remove our n, and then we want to append it to the n. So let's also have some sort of a helper function here for remove. So what we'll have, let's look at remove first. So remove will be pretty simple. It'll be destroying the previous next is now not equal to n, but instead equal to n.next. So we're skipping 1 over. And then the n.next previous is now equal to n.previous. So if we had x, y, z, and we're removing y, all we're doing is we're saying y's previous next is going to point at z instead, right? And then the next previous here is going to point at x instead. So basically we're removing ourselves from the equation and then pairing them up like that. Okay, so that will be removed. And you can see here is the nice part about having these 2 bogus nodes is that I don't have to worry whether or not n.previous is null or not. I can always assume that previous and next exist because I have these 2 guards at the end and start of my linked list. Okay, so let's look at append. We want to append our node to the very end. So we have some sort of a structure like this where we have our previous, our n, and then our tail. This is where we start off with, and this is where we want to be in. So tail, let's look at this. Tail.previous.next, we want to assign it to n first so that we form list link. And now we can say n.previous is equal to tail.previous. So that gives us list link. So now they're linked together. And now for the tail, so n.next is going to be equal to tail, and then tail.previous is going to be equal to n. Okay. That looks correct. And now all we're missing is this eviction thing. So remember the head of our list, so the least recently used is not head, but is actually head.next because head is bogus. So what we'll do is we'll just remove head.next, and also remember to remove it from our map. So remove head.next.key. So map identifies by key, so we pass in the key, not the node here. Okay, let's give this a go. Missing return statement here. Okay, one more try. All right. Oh, looks like there's something slightly incorrect here. Let's see where it is. Let's make sure that we remove it from the map first, because this remove might change the linked list. And I think that's it. Okay. Yeah, that was it. Okay. So that was the change, because removing this head.next, it kind of messes with our linked list. So this head.next.key might not be what we think it is after that call. All right, it's accepted. So, with our linked list and with a hash map, we're kind of guaranteeing that this is an O of 1 call and this is an O of 1 call. So all of these are just pointer manipulation. So these are O of 1. So this is O of 1, and then everything is O of 1. All right, that's the end of today, and I'll see you on the next one.